To all the future Mr.
Hey!
students,
I
do
believe
not take this class.
you're too loud, John. Be quiet.
Too late.
Okay. So, I get that number 4 is weird because we have not really gone over this, but we'll do it here real quick. This is something I want to talk about today anyway. Check this out. You guys are going to love this. Maybe not. We got this coming out like this, something like this. This is a really bad drawing. Hey, you do have 100% right now. Nice work. Something like that, and then we got this one that comes out like this, whatever, okay, right, boom. And they hit right there. So they hit at 1, and they hit at 0. Okay with that? So, you know how we usually do rectangles that go from, hello, what's up? Tell Flick to get his own calculators, man. Yeah, there's 2, I guess there's 2 in there maybe. Yo, do you know how we usually do our rectangles vertically because we're always dealing with f of x? Well, in this case, we have 2 different f of y's, which is weird. This one over here is 12y squared minus 12y cubed, and this one over here is 2y squared minus 2y. Now that seems weird. You could basically, guys, just turn your whole thing sideways. Like you could turn your screen sideways, or your book sideways, and it looks just like a normal graph. But what you're really going to do here, because what's changing now isn't the x values, it's the y values that matter. So our rectangles aren't going to be going up and down. They're going to be going left to right. So you can think of it like our rectangles that we're going to put in here are going to, are you kidding me? Are going to look like this. Does that make sense? They're still super thin rectangles. All right, and we want to add them all up. Look, there's rectangles all over this thing. There's rectangles down here. Like I'm not going to draw them all. That would take forever. But there are all these rectangles in here. We're going to add up all those rectangles. That's going to give us the area. Does that make sense? John, you're smiling, which is great. What's the area of a rectangle, John?
The area of length times width.
It is length times width. Check this out. It's length times width. Add them all up. That's what we're doing. That's what the integral does. Okay? But what's the length of these? Normally the length we said was dx because we're crushing the x down, right? We're not crushing the x's down here. What are we crushing down? The y. So instead of talking about length first, let's talk about the width. What's the width of every one of these rectangles if I make them infinitely small? dy. That's going to be the width. And the length is just the distance from this side to this side. Well, that's changing, true, depending on where I draw my rectangles. But regardless of how it changes, the right side is always 12y squared minus 12y cubed. True? And the left-hand side is always 2y squared minus 2y. Well, how do I tell how far apart they are, how long that distance is? You subtract them. Because if one was 8 and the other was -6, we'd say that they are 14 apart, right? You would subtract them. So the length of these things is just going to be 12y squared. Okie dokie, what is that? 12y squared minus 12y cubed. I got to move this dy out of the way here. Minus, does this make sense? Whatever's on the left there, what is it? 12y, 2y?
You said to make the functions equal to each other.
You would set them equal to each other if you want to know where they intersect each other. True? So look, hold on here. That right there, even though it looks really big and scary, that first thing in the brackets is the length of every single rectangle. The dy is the width of every single one of them. Does that make sense? We want to integrate that. Let me erase this line. From where it starts to where it stops. And that's when you'd set them equal to each other because you want to know what's this y value here and what's the value up here at this one. Where do they hit each other? But in the picture, they show you the bottom of that. And so instead of going left to right now, because we're doing it in y's, we have to go from bottom to top. Does that make sense? We have to say, where's y going to go? Because we're doing it with respect to y. With respect to x, we'd say where x is going. Well, x goes left to right. Y goes up and down. So what's the very lowest y value for the shape we're interested in? It's 0. And the very highest one is 1. And you're going to put that into a calculator. Now, your calculator doesn't know anything about letters. It just knows symbols that you're telling it to use. So when you type it into a calculator, you're going to put in x's. But don't worry about that. Just put in x's where you see all those y's and do that integral. That's going to give you that area. And essentially what you're doing is the thing I said in the very beginning. You're kind of turning the graph sideways, sort of, and finding the area that way. But it's the same shape. That make sense? So anytime you have x equals and there's a bunch of y's in the equation, you're going to have to do it in terms of dy instead of in terms of dx. And we'll talk about that a little more when we do rotations here. What else from the homework? Number 5. Since there are, so let me stop this.